In general, non-ferrous metals like copper and aluminium are much weaker than ferrous metals. You can prove it with a simple tensile test. Using testing equipment to stretch the metal, the force needed to break it can be measured. The dial shows the amount of force applied. Mild steel has greater tensile strength than the non-ferrous samples. Non-ferrous metals are therefore seldom used in their pure form in components that may be subjected to tensile or shear forces. They have, however, one great advantage over most ferrous metals: an ability to resist corrosion. They don't rust or oxidize easily. These samples of mild steel, copper and aluminium have been put into a heavily corrosive atmosphere which accelerates the normal processes of corrosion. When the samples are removed after a few hours, the non-ferrous metals have corroded slightly. In the case of aluminium, the oxide formed provides a protective coating. But the mild steel is very badly rusted. Copper has several desirable properties. It has good electrical conductivity and is very ductile. In its purest form, copper is produced by the expensive process of electrolysis from a mixture of imported blister copper and scrap metal. This mixture goes through a series of furnaces until it becomes 75% pure. It's then cast into large copper anodes. At this stage, most of the impurities have been removed. The shape of the cast anodes allows the heavy copper slabs to be easily transported for the final purification. After cooling, these anodes are placed in large tanks ready for electrolysis. Separate, pure, thin sheets of copper, which act as cathodes, are placed into the tanks, which contain dilute sulfuric acid and nickel salts. Then a high current with a low voltage is applied. During the next 8 to 10 days, the current is carried from the positive anode to the negative cathode in the form of positively charged copper ions. These are attracted to the cathode, and when the process is finished, the cathode has increased in size and is now virtually 100% pure copper. The finished cathodes are removed, and having an electrical conductivity second only to silver, they're ready to be used in other industries. Some are remelted, and using a process known as continuous casting, formed into long copper billets. Once cut, the finished billets form the basis of many processes requiring a pure form of the metal. If the properties demanded by industry include better tensile strength, then copper must be mixed with other metals, alloyed. Brasses are copper-based alloys in which the main alloy additive is zinc. They're either made from virgin metals or are reclaimed from scrap. The assorted scrap brass is added to the furnace. There are two main forms of brass, alpha beta and alpha, the difference lying in the zinc content. After test sampling to check the proportions of the constituents, extra alloying elements may be added. In this case, the furnace, which was producing alpha-beta brass, was found to need more zinc. This is added in the appropriate amounts. The furnace will then be tapped and the molten brass continuously cast to form billets. After they're cut to a workable size, the temperature of the billets is raised in an induction heater to make them suitable for extrusion. The billet, having been heated to 700 degrees centigrade, is then fed into the extrusion press. Once in place, a great deal of pressure is applied. The billet is squeezed through a die and gradually forms a long extruded bar. A wide variety of shapes can be formed, including brass coils, which are fed onto prepared reels, rather like spaghetti. The dies are made of 10% tungsten alloyed steel and can be designed to produce the exact cross-section needed. The finished extrusions are suitable for a wide range of components, which can then be hot forged. The hot working properties of alpha-beta brass come from the structure of the metal, magnified here 100 times. Because the alpha-beta brasses contain more than 37% zinc, this appears as dark beta granules within the alpha structure. This makes the metal relatively brittle, and it needs to be heated before working. If, however, the amount of zinc is lowered, the dark beta granules dissolve or disappear, and the alloy is then known as an alpha brass, which is a ductile metal and can be cold worked. The best known is 70-30 brass, containing 70% copper and 30% zinc. These brasses are ideal for making a wide range of products. Because the brass is so ductile, it's easily cold drawn into wire. The annealed brass coils are first of all pickled. This involves immersing them in a variety of chemicals, a process which cleans and prepares them for the drawing process. It's done on a series of spools. The brass is fed in one side and drawn round spools, each revolving slightly faster than the one before. The wire is drawn out to form longer and thinner reels, ideal for many follow-up processes. One use for alpha brasses is in electrical sockets, where the conductivity of brass, although less than copper, is safe and acceptable. It has the advantage of being a cheap material and is reasonably resistant to wear. Bronze is an alloy of copper and tin, and its use dates back to antiquity. Whole civilizations were indebted to the ease with which it could be worked and cast. These items were produced many years ago by our ancestors who were skilled craftsmen. For them, bronze was an important part of everyday life. However, these days, due to the high price of tin, bronzes are only used where no other alloy will do. Bronze is still widely used to produce coins of our realm and many others. Its properties are ideal. It has good corrosion resistance and wears well. The coins start life in the form of carefully measured alloying elements like copper, tin, and zinc. These are melted at 1,350 degrees centigrade to form the alloy, which is then continuously cast into a long bronze strip. The strip is then cold rolled. The thickness is dictated by the thickness of the coin which is being produced. The rolled bronze coils are now ready for blanking, a process which forms the blanks onto which the familiar heads and tails are stamped. The metal left over will be recycled. Before pressing, the blanks are annealed to soften them. This takes place at a temperature of 600 degrees centigrade. After this, the blanks are cleaned in acids to prevent them from tarnishing. The coins will then be ready for the final process, where the faces are pressed on with steel dies which bear the reverse of the coin's final design. Aluminium is one of the lightest metals, having approximately 1/3 of the density of steel. It's very ductile, has high thermal conductivity, good electrical conductivity, and resistance to corrosion. Although its electrical conductivity is less than copper, its lightness makes it very suitable for overhead electricity cables. However, aluminium lacks strength. If we take a closer look at the cross-section of an overhead cable, we can see that it has to be reinforced by a steel core. Pure aluminium isn't able to support its own weight. To improve its strength and hardness, aluminium is alloyed with magnesium, manganese, copper, and silicon. The alloys produced can be either wrought or cast. The choice of alloy will depend on the properties required in the component being produced and the process used in its manufacture. Wrought aluminium alloys are used to make forged components. The first stage in the forging process is to continuously cast the alloy to form billets. The alloy used to produce these billets contains copper, magnesium, zinc, and silicon. When used in the appropriate amounts, these elements allow the alloy to be heat-treated, as well as imparting the necessary strength to the aluminium. This billet will eventually become part of a jet aircraft's undercarriage. First, it's shaved. This removes the outer layer of impure alloy, which is formed during the sudden cooling you get in continuous casting. The shaved billet is then cut into the appropriate size, ready for the next process. After being heated up to 470 degrees centigrade in an induction furnace, the billet is removed and placed in a 5,000-ton press. This slowly restructures the billet, altering its grain structure from a cast metal into one that's wrought, a process known as upset forging. press also gives the initial shape to the alloy, hinting at its ultimate role and preparing the structure for its final pressing. After reheating, it's ready for the specialized die which holds the impression of the component. The 12,000-ton press slowly brings down the top of the die to mold the alloy into its final shape. Once removed from the press, the shape is recognizable. All that remains is to remove the flash formed in pressing with an electric saw. The scrap metal will eventually be melted down and reused. The final stage is heat treatment to strengthen and harden the metal. After the initial process, the alloy tends to consist of two different items. The major part is called alpha, in which the elements have combined as one. Inside this are larger, hard, brittle components called beta, shown here as the dark areas. Normally, beta is a compound formed by the precipitation from the basic mixture. Since the structure is brittle, heat treatment is necessary. This recombines the constituents to form one material, a process known as solution treating. The material is then quenched to room temperature in water, retaining its form and structure. After quenching, the alloy is very soft and in a similar state to annealed steel. If it's left at room temperature for a few days, the harder, more brittle component, beta, forms again, but in small areas instead of a few large ones. This process is called natural aging, and the effect is to give strength and hardness to the alloy. One great advantage of these alloys is the high strength-weight ratio achieved by these treatments, and they're widely used where low weight is essential, particularly in aircraft. As can be seen, the wrought aluminium undercarriages have to take tremendous strains without failing. Aluminium alloys used for casting can be divided into the non-heat treatable and the heat treatable types. Whether heat treatment is to be used or not is important in the choice of alloying constituents. Non-heat treatable alloys are used extensively for pressure die casting, sand casting, and in the case of these sumps, gravity die casting. The gravity die equipment is first carefully cleaned and the sand core put into place. The die is rechecked and is now ready for the molten alloy to be added. The alloy used in this process gives a long die life and cuts down the danger of porosity, which can be a problem. Satisfactory casting in aluminium alloys demands that the metal should flow readily to all parts of the mold, that when it solidifies, high shrinkage and low hot strength shouldn't produce fractures, and that the cast structure should be sound. After a short period to allow the mold to cool, the die is opened and the finished casting removed. This process allows the production of complex shapes. Only the minimum of machining is needed after the removal of the flash. The finished castings are not heat treated, as blistering could result due to small areas of porosity which are sometimes present. A large amount of porosity was discovered in this component during ultrasonic screening. This would weaken the structure, so it was rejected. Strength is given to the casting by age hardening. Pistons are produced from heat-treatable alloys. They are initially gravity die-cast in a similar way to the sumps, but on a smaller scale. Copper, magnesium, and other elements are used singly or in combination to aid heat treatment, make the metal more acceptable to high temperatures, and enhance corrosion resistance. The finished pistons, after cleaning and fettling, are extensively heat-treated at 520 degrees centigrade. This is followed by quenching in oil to produce a component with high strength and wear resistance at temperatures of up to 150 degrees centigrade. Titanium is just one of a wide range of metals which can be easily alloyed for specialized uses. Because it's very resistant to corrosion and has a high strength-weight ratio, it's found a lot of favor in the aerospace industry. New surgical operations in which artificial joints are implanted in a patient have been made possible by the excellent qualities of titanium. Titanium is usually forged. Here it's being preformed to make part of an artificial hip joint. The preforming roughly shapes the final joint and improves the properties of the metal. The parts will then go on to be drop forged using a specially shaped die. All that's needed now is a little machining. As with all specialist metals, titanium is carefully cleaned and checked at all stages of production so that any faults can be detected as early as possible. Hard wearing, titanium's high resistance to corrosion means that once implanted, it should last for a patient's normal lifetime. This is a typical example of a titanium component. It's part of the fuel injection system for the Rolls-Royce RB211. Once forged, the component will then take its place as part of the highly sophisticated engineering that forms one of the most advanced jet engines in use today. It's the ability of metals to combine with one another to form alloys that has given engineers a whole new range of materials to meet the ever-increasing demands of industry.